Hello and welcome to another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 10, Lesson 3 on surface area. So this entire unit is about solids, right? And we normally don't think too much about the area of solids. That doesn't actually make a lot of sense because area is the amount of two-dimensional space that a two-dimensional object takes up. So what do we mean exactly by surface area? Well, we're going to get into that in the first exercise. So I don't want to spoil it right now. That wouldn't be any fun. Let's start by taking a look at the first exercise. Now, all solids we have studied so far have faces that are polygons, right? Whether those faces are triangles or parallelograms or whatnot, but they're all polygons, right? And each one of those faces has its own area because all the faces are two-dimensional objects. And that gives us a little bit of hint about what surface area is going to be. But let's dive into exercise number 1 and talk about it. A right triangular prism is shown below in two different views. Letter A, how many faces does this polyhedron have? All right. A polyhedron is just a fancy word for like a solid, okay, that's enclosed by polygons. All right, at the end of the day, you don't need to know what a polyhedron is, but this thing is a prism. All right, so how many faces does it have? Pause the video now and quickly count that. All right, well, it's simple enough, right? We've got 1, 2 triangles and then 1, 2, 3 other lateral faces, so we've got 5 total faces. Simple enough. Make sure that that looks like a 5 and not a 6. There we go. A little bit better. All right. Now, letter B, important. How do you know that the lateral faces of this polyhedron are rectangles? All right. So we know that the two bases are triangles because it says it's a triangular prism. But all of the other faces, the lateral ones, that you really kind of think about more in this sort of view, right? Because now here it's actually lying on one of its triangular bases. How do we know all the lateral faces are rectangles? What tells us that? Pause the video now. Well, what tells us that is that it's a right prism, all right? The fact that it is a right prism. All right, whoops. Right, anytime you're told that a particular prism is a right prism, right, then that really kind of means, technically, that the height is perpendicular to the base. Right? And because it's perpendicular to base, all the heights are perpendicular to the base, which makes all of these angles right angles, and all of those lateral faces, that doesn't look like a right angle, but there we go. All of those lateral faces are now rectangles. Now it's a little bit tricky because the two triangles, as indicated on the picture, are actually right triangles all by themselves. So it may seem like this name is basically saying, oh, we got a right triangle as its base, and then we got a prism. But a right triangular prism is simply a prism whose bases are triangular and then whose lateral faces are rectangles. Now let's take a look at letter C, very important. Draw each of the faces below and show the dimensions of each. All right, so this is easy. This is literally like if I put up a piece of paper and I kind of traced out this face and then I kind of put it down so it was just two-dimensional, right? What would it look like? Well, it would be a right triangle, right? That would be 6 centimeters tall and 8 centimeters wide, right? Now keep in mind that this is one of the bases, and so because that's a base, there's an identical face to it, right? So I'm gonna draw that as well, right? 6 and 8. I think I'll leave off the centimeters for right now. We can see them on the picture. And now, right, those are 2 of the 5 faces. I've now got 3 rectangles. So what do those rectangles look like? Well, I mean, they look like rectangles. One of them has a length of 10 centimeters and I guess a height of 2 centimeters. So let me draw that one, right? we've got this one that's 10 by 2. All right. We've got another one that is 6 centimeters wide and 2 centimeters high. So that's sort of this rectangle, if you will, and on this picture up here, it's this one back there. All right, let me kind of maybe bring this up here. So we've got one that is 2 by 6. And then finally, we've got the one that's kind of back here, right? And that one is 8 centimeters this way, and again, 2 centimeters that way, because it's the same as this particular length. So finally, we have 8 and 2. So we've got these 5 faces, right? 3 lateral faces and 2 identical bases. Now, letter D, no great surprise here. We're going to find the area of each face and we're going to sum them all up. And that sum is known as the surface area of the solid, right? So that's all surface area is, by the way. Surface area is simply the sum of the area of all the faces that enclose a solid. And it makes a lot of sense, right? It's the area on the surface of a solid. Okay, we live on the Earth, right? We live on the Earth, which is an idealized sphere, or better yet, we can kind of idealize the Earth as a sphere. Obviously, the Earth has a huge, huge volume, but the surface of the Earth itself has area to it. All right, quite a bit of area. We're not going to get into that right now. Let's find the area of each one of these objects. Now, I'm going to number them. That's a really good way to kind of keep track of surface area. Because often with surface area, there are a lot of calculations you have to do. You want to make sure you don't leave out one of the faces, right? But here we go, right? So for the first one, right, I'm going to put an A with a little 1 down here. That's a triangle. And we all know that its area is going to be 1/2 times its base times its height. All right? Right, we could do 1/2 times 8 and get 4. And 4 times 6 is going to be 24 square centimeters. Now, one of the great things is that at least with surface area, a lot of times areas repeat themselves because you definitely have these 2 bases that are identical. So area number 2 will also be 1/2 times 8 times 6, and that'll also be 24 square centimeters. Now for the other ones. Well, all the other ones are rectangles, so their areas are quite easy. The area of 3 is going to be 2 times 10, which is going to be 20 square centimeters. The area of the third one is going to be 2 times 6, or 12 square centimeters. And the area of the fourth one is going to be 2 times 8, or 16 square centimeters. All right. We have literally found 5 areas for the 5 faces that enclose our right triangular prism. Now all we need to do is add them all up, right? And that is always annoying. You know, it's never particularly fun, but I could kind of put them over here, 24, 24, 20, 12, 16. Let's see if I can add these all up without making a mistake. 6 plus 2 is 8. Plus 4 is 12, plus another 4 is 16. 1 plus 2 is 3, plus another 2 is 5, plus another 2 is 7, 8, 9. Looks like I have 96. And specifically, I have 96 square centimeters. That's it, right? Surface area, in theory, is an easy idea, right? Every single face that encloses a prism or any figure that we're working with, right, is 2-dimensional. And they're always going to be rectangles, parallelograms, triangles, things that you can find the area of, especially after the last unit. Once we find the area of all the faces, we simply add them all up, and that's our surface area. Now, a lot of times these calculations can become annoying, long. Adding them up can take space. Don't hesitate to have a spare piece of paper at your side where you can be doing these calculations with a lot of room. Because if our worksheet doesn't give you enough room, for goodness sakes, get out a spare piece of scrap paper and do the work there. All right, let's do a little bit more work with surface area. First, let's formally define it. What is surface area? Surface area is the sum of all the areas of the polygons that make up the faces of a solid. That's it. So whatever the faces are, you can simply add up all their areas and you've got the surface area. Now, a useful tool to help visualize surface area of a solid is what's known as a net, okay? And we can think of a surface area net as a two-dimensional shape that comes from unwrapping a solid. So let's take a look at this idea of a net in exercise number 2. Let's consider the simple cube shown. How many faces does a cube have? Each face is what type of a figure? All right, this is easy and we talked about it in the last lesson. All right rectangular prisms, boxes. All boxes have 6 faces, right? And you know, you can count them. 1 on top, 1 on bottom, 1 on the left, 1 on the right, 1 on the front, 1 on the back, right? There's 6 of them. So we've got 6 of them, and they're all, in the case of a cube, they're all squares. All right, every single one of them is an identical square, right? A 3 by 3 square. Now, letter B. Draw a net of the cube. There are many. Imagine making cuts along certain edges that would allow you to unfold the faces without them falling apart. All right, so like literally, right? A net basically is like taking pieces of paper, right? Kind of gluing them to each side and then letting them unravel as if they were wrapping paper with absolutely no waste. Because, you know, with wrapping paper, I don't know about you, with me, there's a lot of waste as I start to wrap a present, right? But on this, literally, I can unfold it. What I'll oftentimes do when I think about this is I'll think about keeping the base that it's literally sitting on, just kind of, that's the first thing I draw, right? Then I sort of think about unwrapping the sides. So maybe I let that side fall down and I let that side fall down and maybe I let the top fall down afterwards, right? And then that gives me something like this. Now remember, at the end of the day, there should be 6 of these squares, right? What I'm doing is I'm unwrapping the faces. Now, there are 2 final ones, right? And if you will, they're the front and the back. Those could literally go anywhere, right? They just have to kind of go wherever you want attached to here. Now again, that is one of many different surface nets for this. You could actually take these 2 squares, you could put that one there, you could put this one all the way over here, you could put it over here. It doesn't really matter because when you wrap this thing up, those 2 that form sort of the front and the back can go in a variety of different locations and it's still gonna fold up properly, all right? But if you think about just kind of like folding up all these sides, eventually you'd be able to take these 2, fold them up, and they would sit. Now, why are surface nets helpful? You know, for some students, they aren't, all right? But they are a required part of the curriculum, all right? We didn't use one in the last problem. We could have, but we didn't. But what they do is they give you a 2-dimensional object that you can now find the area of, right, that will give you the surface area of this 3-dimensional object. So, letter C. What is the common area of each face? What is the surface area of each cube? Or sorry, what is the surface area of the cube? Not each cube, there's only one cube up here. So this is actually a very easy surface area problem, right? Each one of these squares measures 3 inches by 3 inches. So what is the area, let's say, of that individual square? Pause the video now and write that down. All right, well, the common area of each face, all of them being squares, right, is going to be 3 times 3, or 9 square inches. That's the common area of each face. But the beautiful thing about a cube, I mean, the spectacularly nice thing about it, is it's got 6 faces that are all identical. So the surface area of the cube, and we oftentimes abbreviate surface area with a capital S, capital A, hopefully for obvious reasons, will be 6 times 9, or 54 square inches. And a cube, again, a cube is the nicest object to find the surface area of. quite frankly, because you find the area of one of the 6 faces and then you multiply by 6 because all the faces are identical. So if we had a piece of paper that was 54 square inches, in theory, we could wrap this cube with it. All right, let's take a look at one that's a little more challenging. A pyramid. We won't be doing a lot of work with pyramids in terms of surface area, but a little bit here and there. So let's take a look at it. Exercise number 3. A rectangular pyramid is shown with a square base and 4 identical isosceles triangles. Draw a net below for this solid. All right, this is really cool, right? Now, first, before we even draw the net, let's make sure that we understand how many faces this thing has, right? It's got a square as its base that's 8 centimeters by 8 centimeters. And I know that may not exactly look like a square, but they did say it's got a square base, right? 8 centimeters by 8 centimeters. And then we've got 4 triangles, right, that are isosceles, meaning they've got 2 sides that are the same length each. So what does this thing look like if I unfold it? Well, originally I might draw that square, right? And that's going to be 8 by 8. It's good to have those kind of dimensions there. I could also put them on the outside of the square. The only reason I didn't is because then if I start to unfold the pyramid, I get an object that looks like this. Right? Now, what do I know about those triangles? Besides the fact that their base is 8 centimeters long, I know that their height is 10 centimeters. And maybe that's better shown on the one that up here that's vertical. Right? I won't draw that in for each one of them because they're identical. Okay? So I've got this square base, and then I've got these 4 identical triangular lateral faces. That was a mouthful. So let's now take a look at letter B. Find the area of each polygon in the net and sum to find the surface area of the solid. Awesome. I'd like you to pause the video and see if you can figure out the surface area of that solid. All right. Well, we've got the square, right? So let's do that one. Maybe I'll label it like this. The square area is equal to 8 times 8, or 64 square centimeters. Now, there are 4 identical triangles. All right, let's just find the area of one of them. Well, that's going to be 1/2 times its base. Let me just bring up here, right? Well, actually, I'll draw it down here, right? We've got these triangles whose bases are 8 and whose heights are 10. So it's going to be 1/2 times 8 times 10. 1/2 times 8 is 4. 4 times 10 is 40. 40 square centimeters. Now, keep in mind, though, we do have 4 of these, right? Now, you could either say, well, I've got 64 plus 40 plus 40 plus 40 plus 40. Or you could do the 40 times 4, get their total area. So maybe I'll do that. Total triangle area equals 4 times 40, which is 160 square centimeters. So now my surface area will be 160 plus 64, right? And that's going to be 224 square centimeters. Let me make sure everyone is clear about the fact that that is my surface area. But again, all we had to do was simply find the area of all 5 faces, right? 64 square centimeters for that square, and then 40 square centimeters for each of the triangles, 40, 80, 120, 160 in total. 160 plus 64 gives me a total surface area of 224 square centimeters. Each one of the calculations is pretty easy on its own. It's just making sure that we've kept track of it all. And that's where a net can be helpful, right? Because it can really say to us, oh, okay, I've got to remember that I have 5 areas that I'm adding up here. And it's a little bit easier to maybe look at this picture than it is at this picture. All right, let's wrap this up. So today, we learned about the idea of surface area. And it should make a lot of sense, right? Area is a measurement of the space inside of a two-dimensional figure. And although we're working with three-dimensional figures, what encloses the three-dimensional shape are two-dimensional polygons, right? Things like rectangles and triangles and squares, okay? And we can find their area. And when we add up all the area of all the faces that enclose a solid, we get the surface area. A net, right, a surface area net, which is just an unwrapping of all the faces and kind of laying them flat so that we can really see them, helps us visualize that two-dimensional surface that's really wrapping around our three-dimensional solid. It can also help us in simply keeping track of all the different areas that we might have to add up in order to find surface area. All right, we'll work a little bit more with surface area in the next lesson. For now, I just want to thank you for joining me for another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.